Okay, so now we're going to go quite simple and illustrate how, even in this very simple context of a static game, you can still have lots of problems. Okay, so I'm going to talk about the issues involved in estimating dynamic or discrete choice games of incomplete information with this multiplicity of equilibria. And, we have been through like a whole variety of different estimation methods this week. And we're going to try to see how these different methods compare in this very simple static context. By the way, these are essentially some slides that are based on a paper by Qilin Su that's in the box. It's called, this title. Qilin was like the founding father of this constraint optimization approach to structural estimation, together with Ken Judd. Unfortunately, he's not here anymore, but his method is still here. And I think even though I'm going to try to take some of these, methods to their boundaries, I'm not trying to say that MPEG doesn't work or for anything, NPL doesn't work for anything. Just trying to illustrate some of the difficulties that arise when you have multiplicity of equilibria. Anyway, so we've seen several different ways to estimate dynamic discrete choice models. We're going to apply them here in a static context. And Ariel Pekis and Ostrowski and Berry, they had this nice paper where they compare various different estimators. For the two-step estimators and kind of, show that there's some issues with finite sample biases when you are not accurately estimating the first step CCPs. And so these are different ways to do that, right? So there's, we talked about earlier this week, equilibria and Mura's NPL estimator for estimation of dynamic games, where you start you start estimating the CCPs from the data, and then you kind of update, you estimate the structural parameters given these CCPs. That in turn implies new conditional choice probabilities. And then you just use those as starting values for another two-step estimate, okay? So I'm going to try to illustrate that. So Pessendorfer and Smith-Wengler, they say, okay, yeah, there's some issues with convergence here, and then Kasahara and Sumatsu, they suggested some sort of dampened version of that estimator to accommodate some of the problems with stability of this NPL mapping. What I'm going to present mostly today is the results from Su's paper in quantitative economics, or quantitative marketing economics, and then they have a nice paper where they're doing the same sort of comparisons in the context of dynamic games, where they also compare all these different methods. Anyway, we're going to start really simple. This is a very simple game, right? There's two firms, A and B, and they both essentially have to decide whether or not they want to serve the market. So DA, that's an indicator for firm A, whether they will serve the market. So if it's equal to 1, then they're going to be serving the market. And the same thing for firm B, that's an indicator whether or not they're going to be entering into the market. There's no exit or dynamics or anything. So here's the payoff functions. So here's a payoff if you're entering the market, and you see here, you essentially you get a payoff that depends on whether your competitor is there. So you're going to be knocked over by minus beta if both firms are active in the market. Okay, so if you have a big negative beta, it's going to be a big penalty, and it's going to be like an anti-coordination game. You don't want to be there at the same time. So with these, what we want to do is we want to estimate given data on these observed decisions, whether or not these two firms are active in the market, we're going to try to see if we can estimate alpha and beta. Okay. So XA and XB, they're just observed firm types. They're going to be common knowledge among the two players. We're not going to try to see if we can add any sorts of variation here, but that's what could be in there. We're just going to take that as data. And then there's going to be the extreme value shock, right? Surprise. That's going to be like idiosyncratic shocks to their investment decisions, whether or not they want to be active in the market. And they're going to be private information, okay? And then epsilons are observed by each firm, but not by their opponent, nor by their contrition. So that's kind of just a static version of what we've seen so far. Okay, so you can, well, assuming that they are at extreme value, you can derive the Bayesian-Nash equilibrium equations here. So you basically get these best response functions for either the two firms that depends on the probabilities of their opponent. So the firms that make expectations about whether or not the opponent they're entering into the market. And so they don't observe the actual actions in the same period, but they can derive what the probability that the opponent is serving the market is. In this case, for firm A, well, then you take the expected, calculate the expected payoff, taking into account your expectation whether the other firm is serving the market. So there's going to be a best response mapping for firm A that depends on the probabilities, investment probabilities for firm B, and of course indexed by the structural parameters that we want to try to see if we can estimate, and a similar one for firm B. And so I'm going to try to use the same letter, the psi for these best response mappings. So in dynamic games, of course, these would just be more complicated functions, but here they're very, very simple. Okay, so we're going to do a little bit of Monte Carlo and some examples, and we're going to start here with, very simple, very contestable game. So, so here the monopoly profits that would be, with alpha equal to 5, you'll get this payoff if you're alone, right? And if you have to serving the market together with your opponent, well, you're going to get -11, which is beta is -11 times this observed times. Okay, and then there are going to be 2 observed times. We're just going to take them to a bit different to see see some different choice probabilities of the two firms. Okay. We're not going to try to see if we can estimate that. Here's the intersection of the best response functions for these two firms. You see, in this case, there's like 3 different equilibria. There's one where firm 1 is just investing with a very low probability, and the firm 2 is investing with a higher probability, and there's another equilibrium here. It's kind of the opposite, except because of the differences in the x's, these investment probabilities not exactly going to be the same, and then they're close by. There's a mixed strategy equilibrium. Okay, which is this is an unstable equilibrium, and these are stable equilibria. So what we can do is, if we wanted to do successive approximations to solve this, successive approximations of these best response mappings, that would amount to, like, you substitute one into the other, right? And then you just see if that maps into the 45-degree line. So I've done that here. And so here's what I call the second order best response function for firm A. So that's where I've substituted the best response of firm B into the best response of firm A. You get a mapping from, probabilities of investing for firm A to firm A, and that should be a fixed point. Then you got your equilibrium. And you can see here, you can see here that the investment probabilities of firm A is going to be very low, just like this number up here, and then you're going to have the same probabilities of investment out here for firm 2 for the other equilibrium. It's kind of corresponding to the investment probabilities of firm A here for this equilibrium. And then of course you could calculate what is the best response in that equilibrium for firm B to get that, to get those numbers. And then there is the mixed strategy here in the middle, this unstable equilibrium. And you can see here, if you were doing like successive approximations on the best response mapping, well, you're going to converge to this point. If you start anywhere in this interval, you're going to converge to this equilibrium. You start here. And so there's these two different stable equilibria. Okay. Now, it's very easy to solve in this context. It's not hard to come up with a full solution method for this game, right? This is a very, very simple set of equations we need to solve. And one way would just be like do successive approximation from one end. You're going to find one equilibrium, then do successive approximation from that end. You got to get to the other equilibrium, then do some sort of bracketing in the middle to trace out where if there's more equilibrium, then do successive approximations to see if there's only one in there, and then you go on from there and you can find all the equilibrium. That's a surefire way of solving this model, okay? And it's not that hard. Okay. So we're going to try to see, I mean, we want to do econometrics, right? See if we can estimate those structural parameters, the alphas and the beta. So in order to do so, we need some data. Okay, so we're going to start generating data from a single equilibrium. Look, it's just played out in one of each of these three different equilibria. Okay, so like equilibrium 1, 2, 3, where number 2 is the unstable one, and number 3 is kind of close to one of the unstable equilibria, or to the unstable equilibria. Okay, we're going to assume the two players just playing that same equilibrium over and over again. We're going to generate a bunch of data, fix those x's, and then given the data, we're going to try to see if we can uncover those structural parameters. Okay, so one thing you might do is do maximum likelihood. So here's a likelihood function. It's essentially a likelihood function for standard discrete choice model, except that now the choice probabilities for investing and not investing is going to be a solution to this dynamic static game. And so here you got the two contributions for the two players. So for firm A and for firm B, an indicator for firm A investing times the log of the probability that firm A is investing as a function of those structural parameters. Again, these are like implicit functions of these structural parameters. You need to like solve these two equations here to find find the fixed point you saw in the previous graph, right? So that fixed point is going to move around as you move around the parameters alpha and beta. Okay, so PA and PB are the solutions to these Bayesian-Nash equilibrium equations, and this is going to be the log of the likelihood. Now, see, the problem is there may be more than one solution here. So you also need to kind of maximize over these different equilibria. Take the equilibrium that is, so to say, most in accordance with the data. Okay, so here's what you might do. This is an outer loop. So again, we got like a nested fixed point algorithm in some sense, where you search over those parameters in order to maximize that likelihood, allowing these choice probabilities to depend on the parameters. Okay, and then for an inner loop, for a given value of the structural parameters, you solve the Bayesian-Nash equilibrium for all the equilibria. Okay, so for, all these potential three solutions to get all these three different solutions. In our case, it would be like 3 at the true parameters. So k would be equal to 3. But this could vary as we vary the parameters. Maybe some of the equilibria is going to be knocked out, and then you choose the equilibrium that essentially gives the highest likelihood. That gives you essentially a single valued likelihood for each value of the parameters. And then and then you use that likelihood to when you search over the parameters. So that's it. Let's try to see if we can plot that. And here it is. Here's the likelihood generated from equilibrium number one, nice and smooth. The true value, well, that's right here. Here's the maximum likelihood estimate. We're doing pretty well. True value should be like 5 for alpha, minus 11 for beta. And, you know, we can learn from these data what the parameters are. Yeah? Yeah.
Is there a requirement that only one equilibrium give the highest value of likelihood?
If there's only one equilibrium that gives the highest value, so well, that's that. You know, so what you're asking is that if there could be multiple equilibria that at different sets of parameters could give the same likelihood. Yeah, I can't rule that out. That would result in some sort of identification problem here. You don't know if it's the parameters of the equilibrium selection. I think in this case, it's not going to be the case, but you know, in dynamic games, there's going to be huge multiplicity of equilibria. I'm not so sure. So anyway, I want to illustrate that this is a nice and easy case. We're able to estimate, you know, alpha and beta, just to maximize that likelihood. Okay. But then look at this. This is the likelihood for equilibrium number two. Any idea why we're seeing something like this? This huge cliff here. What's going on? And this valley over here. What do you think is going on in this picture? Yeah. Exactly. Okay. So what happens is, as you change the parameters, you're going to change the best responses. And as you change the parameters, it may be knocking out some of those equilibria, in particular that equilibrium right up here. Those equilibria over here, it's kind of a knife edge that we have two parameters here, or two equilibria up here. If you just move the parameters just a little bit, this curve will go below the 45-degree line. There will be only one equilibrium, which has very, very different investment probabilities. Okay. Now, if the data was generated from those equilibria up here with a very different set of investment probabilities, you change the parameters, well, then you're going to get a huge drop in the likelihood as this curve goes below, right? So now the set of potential solutions, and therefore also the likelihood function, is going to depend on those structural parameters, ability to serve either one or three equilibria in this case. So you're going to get a very ill-behaved likelihood.
So you get the same input for equilibrium 3?
Yes. Yes, we do. Okay, because it's knocking out not only equilibrium 1, but also equilibrium 2, the unstable one, but also equilibrium number 3. Okay. So this is not a feature of equilibrium number 2 being in an unstable equilibrium. It's just it's a feature of that equilibrium simply not existing for certain values of the parameters. Okay. So that's why you also see that problem for equilibrium number 3. How would you maximize the likelihood in this case? Well, let me start over here. This is going to be easy. You just throw Newton-Raphson at it, right? That's you know, you calculate derivatives, you know, and maybe your Hessian, you do your Newton steps and update it, go nicely smoothly to the top, right? But here, it's not that clear I can just use a gradient-based maximization algorithm. I mean, how do you even calculate that gradient here? It's not, I mean, it's infinite, right? So you're going to take a very, very long step or a very small step. Yeah. Okay, so you can't, that's a real problem. You can't use gradient-based methods directly on this sort of objective function. Okay, so we can also do mathematical programming with equilibrium constraint, the constraint optimization approach. And so here's another way of maximizing the likelihood. Remember, we were doing, when we did the hero sucker with impact, we would not only maximize the likelihood function with respect to the structural parameters, but also with respect to this discretized solution, the expected value function. So we're going to do the same thing here. Now the solution is PA and PB, the two investment probabilities. Okay. So we have more variables in our constraint optimization problem. Now, without any constraints, we wouldn't be able to identify both alpha, beta, and the structural parameters. So we need to impose the constraints that this needs to be in equilibrium. So these are going to be the constraints we are imposing, right? So very much like we would maximize the likelihood function for Harrow-Sucker, subject to the constraint that the Bellman equation needs to hold, we are now just maximizing that likelihood function subject to the constraint that the Spatial-Nash equilibrium coefficients will hold. Okay, and we can, we may want to put some bounds on the probabilities and naturally on the unit interval. We can throw that after our constraint optimization solve. Okay, so here's what you get. And actually, it kind of works in this little simple example. Don't make too much of these results, but in each of these different cases, we can estimate the model with the nested sigmoid algorithm or MPEG implementations. So what I'm doing up here is essentially here I have a surefire way of finding all the equilibria, because I just devised an algorithm for you that just calculates all these three solutions, right? And then I just take the upper envelope and, well, I'm just using another algorithm. In this particular example, it's very simple to use just nil-to-meet or something. It's going to find the top of the likelihood function despite the cliff. But of course, if you have a bigger model with many more parameters, it is a challenge that, you can't just use gradient-based methods. Gradient-based methods are usually pretty effective in finding the maximum of the likelihood function. This is a real concern. Anyway, so it seems to work, and it both produces the parameters that we are trying to estimate. Okay, so some remarks. I think we kind of said this, but just repeat. Okay, so we got discontinuity. Yeah.
So the gradient method doesn't work, and what method would you recommend?
So I'm using a gradient-free method here, the nil-to-meet. It's called F-min search in MATLAB. There's several algorithms out there, like some of the the people who have teaching previously here. There's a similar event called SICE. They have some very cool gradient-based, gradient-free solvers called pounders. But I'm just gonna, Fedor, he knows a lot about that. But doing maximization with a gradient-based solver, it's very clear from this picture it's going to be difficult. Okay. So the objective function and constraints is actually for MPEG is actually smooth in its variables. Okay, so you can use gradient-based solvers for MPEG. Okay, I mean there's nothing here that's not smooth, and if you change the parameters and the constraints here, it's just changing smoothly, so you can still use gradient-based solvers for MPEG. Okay, so that's a real advantage. The objective function, well, that's if you look at the objective function for the likelihood function, it's not differentiable and not even continuous, and it's going to create some difficulties in terms of the of making standard inference using the usual theorems you have in your textbook. Okay, because one of the requirements there is differentiability, and how do you calculate the variance covariance matrix by taking the second order derivatives, you know, when the first order derivatives doesn't even exist. Okay, and so another thing to note here is this is an extremely simple problem, right? I mean, if we try to make it more simple, there'll be no model. So these investment problems we are having here on our model is just scalars, right? In a dynamic model, they'll be functions of the state variables, and there'll be one for each of the players, and you know, these could potentially be high dimensional objects. So this is making it much harder to solve for these when they're high dimensional. So that's going to be a challenge, especially for maximum likelihood, the NFXP implementation of a maximum likelihood. You need to find all those conditional choice probabilities associated with all the different equilibria, and they're going to multiply with your multiplicity of equilibria, and it's going to be difficult. Okay, and it's also clear that finding all these equilibria, but just iterating on the Player-Bellman equations, or in this case these best response mappings, is going to deliver, if you start one place, maximum only one solution, right? I mean, that's a feature of an iterative algorithm. With one starting value, you get one solution. Okay, so it's going to be hard to find all the equilibria by just doing successive approximations. Okay, you will have to do successive approximations at least once for each of the different equilibria, and hope you find all of it. Yeah.
So maybe can we explore the result because of that, and like maybe we know that we could have just try to find it's the equilibrium free, and we know maybe equilibrium free from A is investing more than from B, and we just fix that particular equilibrium, maybe it would be a whole
Okay, let me just say one thing. I'm generating this example to show you guys problems. Okay. So of course, first of all, there'll be, you know, for many games, there'll be ways to find all the equilibrium. And second of all, you know, it could be that there'll be some other sets of parameters here that would fit the real data much better. You wouldn't have the problem. It was not that contestable. Here, I'm really hitting the, you know, the duopolist with a hammer, right? They get -11. Instead of 5 if there's two firms serving the market. So it's really, you don't really want to be there at the same time. So, you know, I mean, in problems there will not be this multiplicity of equilibria.
before we go to the next one.
Well, so sometimes you can prove this in a unique equilibrium, like Fedor's going to talk about an example with in a dynamic game later, where we can prove there can be, under certain circumstances, there'll be a unique equilibrium. And there you will have no problem. You can just use these methods out of the box. Of course, whether there will be a unique equilibrium usually depends on the parameters, right? And as you've seen here. And we can actually try to run the code and see what happens if we change those parameters. I have a little script over here. And so why don't we just, this is the code that generated the graphs for this slide, you know, the best response functions. So why don't we just try to say, okay, not make it so hard if you're in the if you're in the duopoly. So we just, instead of minus 11, we're going to get -5 or minus 1. Okay. And then you can do the same graphs. And here they are. Let's just look at those. This, first of all, there's only one equilibrium, right? Second of all, the likelihood function looks kind of nice, at least in the area of the solution. Of course, when you start to explore the whole area, where suddenly the parameters change into an area where there could be multiplicity of equilibria, well, then you start to get all sorts of funny curvature, but around the solution, it looks nice and smooth. Okay, so that was pretty much it for the case where we were just generating data from one same equilibrium from all of the markets. You know, in reality, maybe you don't really know if you have multiple markets, which equilibrium would play in the different markets. We want to try to see if we can, you know, use these methods to estimate models where the equilibria could come from different or could be played from different equilibria at different markets. So we're going to make a little example here with 25 different markets with 25 observed pairs of these XA and XB. So we're going to just let those vary across different markets. We're going to treat it as data and observe, but we still have alpha and beta equal to minus to 5 and minus 11. But, you know, given these different sizes of X's, in some markets there will be multiple equilibria, in some markets there will be a unique equilibrium. Okay, so these have 5 points and they're equally distributed on this interval. Okay, so when essentially when you scale down X, it's a little bit like scaling up the I extreme value term, and so at some point, you know, if X doesn't matter, right? It's just the I extreme value term in there, and that's just like flipping coins. And this is going to be a unique equilibrium. You know, it's just scale up the I extreme value term. So that's the only thing that matters. Well, both firms should just invest with probability 1.5. Right? That's a unique equilibrium. Anyway, so we're going to do this, use the same parameter values, and then for each of these markets, we're going to solve the Bayesian-Nash equilibrium equations for each of these different markets. And then we may, for example, take one particular equilibrium at all the markets, or we may take randomly chosen equilibria at different markets. There are going to be multiple equilibria in most of these 25 markets. I have a little figure showing that. And then, yes, and for each market, we randomly choose 1,000 data points for that market. Randomly choose an equilibrium. So, yeah, so the equilibria can be different across the different markets. Here's a number of equilibria. So as you have very low values of X, you're going to have a unique equilibrium. And otherwise, it's going to be potential multiplicity of equilibria. Okay, so here's how you do it, you know, the nested fixed point way. Again, you would maximize only with respect to the structural parameters. Okay, so you got, you maximize the likelihood for, that's going to be the outer loop, search over the parameters, and it's going to be an inner loop where you solve the model for each of these different values of alpha and beta. Okay, so what does that amount to? That amounts to solving for all the equilibria again. Okay, so there's going to be, for each market, there's going to be, you know, potential 1 up to capital K, you know, 3 equilibria in each of these different markets. So we're going to get, for each market, we're going to get investment probabilities for each of the 2 firms, potentially for several different equilibria that we're going to index by K. Okay, and these are going to be solutions to these Bayesian-Nash equilibrium equation. Essentially, you know, this is going to be the crossing points of the best response functions that we have looked at, you know, so far. Okay, of course, they're going to be different for different markets, right? Because different markets have different values of X, but I think you're going to see that, okay? So, and then we choose again the equilibrium that gives the highest likelihood, okay? And then essentially, the best response probability is only as a function of the parameters, not the equilibrium selection, so to say. It's going to be a function only of these parameters once you've selected the one that maximizes the likelihood over the equilibrium selection mode. So you can.
Biggest clear. So K star is a function of M there. It can be different for different.
Yeah. That's right. Yeah. Essentially, it's a little bit like we have not only the structural parameters, but also this like discrete parameter for each of the different markets that's going to be selected. We take the upper envelope of these equilibrium specific likelihood functions first, and then we search over the parameters, the structural parameters of that upper envelope.
It's kind of like an equilibrium fixed effect or something.
You can say that. Yeah, that's definitely what it is.
I have sort of a question really about these big credentials to behavior. I don't think you can show them maximum likelihood is efficient because the theorems on maximum likelihood is given new probability for each alpha beta, each set of parameters. So what you're doing really is getting an outer probability. You're getting because it can be a given alpha beta, it can be any of these things.
Mm-hmm.
Okay, so I'm going to get a probability that is all these. Actually, in reality, there was a unique thing that happened. But it's like in moment inequality, you're getting a set essentially. So I think, and I never quite understood this, but what I don't understand is the push to maximum likelihood because it's not necessarily. I mean, we don't have it. At least I don't know a theory of the other probability being efficient or anything like that. So it's true that I believe that you can show that you consistent should get it on. But I don't know why. So this literature's gone like that, and I never understood why maximum likelihood should be better than anything else. I mean, not anything else, but some other consistent estimates.
So you're thinking, what do you think have in mind in terms of comparison, like two-step estimators, or?
Yeah, I don't want to argue with this. Because I have one in it, and I don't really care.
Okay.
Victor has a couple, but I think it's an interesting question of why.
One of the things that you see with the two-step estimators, I'm not going to show it, but is the Bayesian equilibrium equation. Well, they're not necessarily going to hold, so you don't impose the equilibrium when you estimate the model, right? So
I think there's some sense in it.
Both of them are consistent, right? Because as you get more data, you get the right choice probabilities.
Quite all most of them. But I never quite understood. So there's no theory for efficiency. I don't think. If there is, I don't know. And I don't know. I don't know if you guys have ever thought of this. I've never really put it down or anything, but it's always bothered.
No, I guess I have to confess, I just assumed maximum likelihood would be efficient, but
if every market, if the asymptotics are markets going to infinity, every market could have a different equilibrium. Let's constraining it as a finite number of equilibrium in any possible market, then there's going to be a mixture. Some fraction are going to be equal to 1, 2, and 3, and you won't have an incident. The worry is you could have an incidental parameters problem where the number of incidental parameters are growing with the sample size. And I don't think you're going to have that. I think you can prove consistency of maximum likelihood here.
I don't think you're getting it. I don't think you're getting an actual probability of that. You're getting an outer probability of that. I don't think there's any difference. For any alpha beta, right, you're going to check. I think it's good. You're doing better with everybody else because they just chose one. Okay. And what you're doing is you're getting, alpha beta can generate 3 different equilibria and get the probabilities of one of these 3. Or you need one of these 3. And I think that's good. You should get it wrong. But I don't see the efficiency on it.
okay, I'll be careful with the claiming efficiency then, okay?
But you can't do a Monte Carlo and just see empirically what's more efficient, right? And I think in the Monte Carlo, it is more efficient, right?
Yeah, here it's going to be very difficult to see because the data we generate is going to be more than enough to very accurately estimate these investment probables is just two numbers, right? So, but I think we'll see more in the dynamic game later that it matters in terms of size of standard errors. Okay, so you can also do this with MPAC, and so now the constraints optimization formulation is the following. But note here now the alpha and betas, they are they're still there, but then you have investment problems that not just scalars is going to be one for each of the different markets, because we're going to have more parameters in the constraint optimization problem, and then you just have to impose the Bayesian-Nash equilibrium equations for each of the different markets. And the benefit here is that MPEG does not explicitly solve the Bayesian-Nash equilibrium equations to find all the equilibria at each market for every trial parameter of the parameters. Okay, so where that would be what you would do with this nested fixed point approach to maximum likelihood. Find all the solution every time you change parameters, find all the solution, and do it again, find all the solution. Take the kind of upper envelope of the equilibrium specific likelihood functions. So here the number of variables is then much larger, of course, right? Because they're going to be 25 as many of these equilibrium parameters. Okay, so and in principle, it's just going to implement the same estimator, maximum likelihood estimator. Okay, so here's what you get with NFXP. Sorry for the scaling here. It's supposed to show that it kind of works and find the right parameters and identify the true underlying equilibrium. That's another graph. Here's what you get for MPAC. Sometimes it kind of shoots off and find crazy numbers. And what I want to emphasize here, you see there's some blocks out here with some parameters that are far away. What I want to emphasize here is that these are solutions to this problem. Okay, so here the Bayesian and Nash equilibriums hold, and you have found a local maximum to the likelihood function. Okay, so it's not like it didn't converge or something and just create, throw out something crazy. The Bayesian Nash equilibrium equations are actually satisfied in these solutions. So what is happening is it's just finding a local maximum. Okay, so so you can say in some sense the nested fixed point algorithm, where the problem there is the lack of differentiability. It's really hard to find that maximum using gradient-based solvers and do the max. It's hard to find all the equilibrium to calculate the likelihood function in the first place. But if you can do that, then it works. Okay, so it works better in this particular case. So I'm not trying to say that maximum likelihood would just always work. If you have more parameters to estimate, it's going to also be difficult to find something that converge. But here, at least you have to be careful when you do this constraint optimization approach that you actually find the global maximum to the likelihood function. So the problem is you can get local maximum. Okay, so yeah, here the implied investment probability, the true one minus the estimated one, and you can see it's not always getting the implied investment probabilities right. In fact, some of them are completely off over here. This is still equilibria, but they are just arrived at some local maximum of the likelihood function. Anyway, so here's just a little bit of wrap up. If we want to compare in these cases with multiple markets, NFXP, well, there was two parameters in the optimization problem. Here you have 2 + 2 times the number of markets, because all these investment probables, they are multiplying. There's going to be one for each of the different markets. So the number of variables in the constraints optimization problem is going to increase. We can still do it, but it's going to make it all the more harder to find the global maximum of this of this likelihood function and imposing the constraints. Yeah, so we can actually back out the equilibrium that was played in the data, but there may be issues like you kind of alluded to in the beginning, or I guess it was you. There'll be observationally equivalent parameters where you can move around the equilibrium selection rule and the parameters. Okay, so we're not so that's going to potentially be an issue here. What the main thing about the NFXP implementation is that the main drawback is that it needs to find all the equilibria at each of the different markets. That can of course be hard in more complex problems. Of course, here we are solving for all the equilibria anyway, so we're just like reusing them. Okay. And so here the flip side of that problem is you can have local minima with many markets, and of course, if you have lots of data for each of these different markets, that would translate into we have very, very good starting values for the investment probabilities, right? The P's. We can estimate that off the data. They're very precise in the beginning. You have good estimates, good guesses for what the parameters might be, say from a two-step estimator. Then maybe MPEG would not perform so badly, right? In those contexts. So I think the message here is, we have so many different tools. Each of them have different strengths, and as I'm going to show, the two-step estimators has the strength that it's not going to have to borrow with all these different equilibria. So you can have some sort of consistent estimates for the alpha and beta from a two-step estimator, go out, estimate the choice probabilities directly from the data, initialize your MPAC estimate, implementation of the maximum likelihood estimator, and that's going to be a use of several methods if you want to obtain your maximum likelihood estimate. So, okay, so here's a little disclaimer. It's not maybe, the best implementation of MPAC. Of course, you would need the right software and everything, okay? So it could be that some other maximization algorithm, constraint optimization algorithm was better in finding the global maximum. But the one I used in MATLAB was not able to do it, and it kind of fooled me. You look at the estimates, and it looks like its solution to the problem because the Bayesian-Nash equilibrium constraints are satisfied. But how can you know there's another place of the likelihood function? Well, you just have to search for different starting values. Okay, now, so there's going to be various different ways to do two-step estimators. Okay? I'm going to mostly focus, so there's a two-step estimator where you start estimating the conditional choice probabilities, you throw that into the best response mappings, and then you could do like least squares or minimum distance or pseudo maximum likelihood. And so I'm going to kind of skip a little bit through this here. I think we, yeah, well, anyway, let's talk about the pseudo maximum likelihood, just for concreteness. So the step is you estimate the CCPs, then you essentially maximize the pseudo likelihood. Wait a second here. What am I doing? Yeah. I'm plugging in I'm initializing or fixing the investment probabilities from the data, from the CCPs I estimated from the data, and then you just maximize that pseudo likelihood.
Like Victor's lecture for single.
Yeah, exactly. So you or Bob's, you can say too. So you estimate the CCPs, throw them into the best response mappings. That's going to give you investment probabilities for each of the two firms, and you use that as the likelihood. And that kind of boils the whole thing down to a single agent problem, because you in some sense you're playing against the data, right? The investment probability is implied by the data and not something that can move around. Okay, and since these are consistent estimates, it should kind of work. Okay, now there may be an issue with small sample bias, right? That you maybe you don't really get those as first step estimates accurately in a finite sample. So that's gonna result in the right hand side and the left hand side of these equations not necessarily the same. Okay, so it's not necessarily an equilibrium in a finite sample. It's not maybe an equilibrium, but it's the Bayesian-Nash equilibrium equation is not going to hold exactly. Okay, so we haven't imposed the entire structure from the model that that these players' actions are equilibrium investment probabilities implied by the structure parameters. So in that sense, I think maximum likelihood should be imposing more structure from the model.
Therefore more efficient.
And therefore more efficient. That's what I would think. Yeah. Anyway, so the idea with Victor's paper was to, if we are estimating these CCPs in the first step with some, not fully efficiently, then maybe we can improve by using the implied investment probabilities that come out of the best response function estimated, indexed by the parameters we would have estimated with this first step maximum pseudo maximum likelihood estimate. Okay, so here's the algorithm, right? You go out, estimate this from these investment probabilities from the data. Okay, then you essentially find the you estimate the alphas and beta using the pseudo maximum likelihood estimator, where you have fixed the investment probabilities at the estimated values, and then you move around the structure parameters to maximize the pseudo likelihood. Now, this is a very simple problem to solve, right? Because in this case, it's a logit, right? It's the likelihood function is globally concave. It's just going to nail it. It's no problems with lack of differentiability or anything like that. It's just going to take us right to these to the maximum of this objective function. So that's very desirable. And so now, if you do that once, you're going to get the two-step CCP two-step CCP pseudo maximum likelihood estimate. That's the one, the potential be inefficient and subject to finite sample bias. So what then Victor is proposing is that you do another iteration of the best response mapping, okay? To now predict what would the investment probabilities be at those estimated parameters, okay? If this is, if this is already, if these equations already hold, you're done, okay? And there's no need to impose further structure for this equilibrium. But if not, you're just going to plug that in the next round, and then you kind of sequentially update the estimates. You get like a sequence of estimators, okay? And the idea is that you should converge to the maximum likelihood estimate. Okay. So you think this thing, if you look at this thing as like one organism, right? These two things as one step, it's essentially a mapping from choice probabilities to choice probabilities, where in there you are re-optimizing the parameters. Okay, you're solving the parameters, but you put some CCPs in, and then you get some CCPs in. Okay, sorry for calling them CCP, they're not really conditional on anything here. They're just P's, okay? So yeah, okay, yeah, fair enough. But this little example. Okay. So in what this algorithm is suggesting, just like Victor said, it's like you're doing such successive approximations on the NPL mapping. Okay. If that mapping is not a contraction, we're not really sure it's going to converge and you're going to find a fixed point on the LPL mapping. But there may be other ways to find that fixed points. Nobody says it has to be solved using successive approximations. You could use, in this case, we would we could just use Newton's method to solve that set of equations, solve for PA and PB. And in fact, the result I'm going to show you for the sequential estimators shows that it doesn't really work all that well. But I was using the successive approximation algorithm to a way to achieve that estimator. It's just not the best implementation. It would be much better to do what Victor proposed with the what was it called, the spectral algorithm. Anyway, so here's what you do. You get with NPL for equilibrium number 1. It doesn't look all that good for equilibrium number 2.
Just back to the two-step measure.
Yeah.
So in a step 2, the way to use variance covariance measure for estimate. I make a condition on step 1 estimate or handle it.
Yeah, so there's going to be some sort of correction for two-step estimation error. What do people do? Do they just do like bootstrapping or two things?
Why don't you simulate from the original thing and do it time and again, the original parameters estimated. Another distribution that normally draw from the normal pushes run through. There's out of it. You'll get the right things. The other thing you can do is you can, no it doesn't, but there's a semi-parametric approximation. You can take the derivative and then get the derivative of the or for shorting. There's the likelihood for shorting the effective vector space parameters. And then, and then just with the normal extension. Either one of these two.
Yeah, so I guess yeah. Okay. NPL worked beautifully for equilibrium number 1. It's very much separated from those two difficult ones. Okay, and by the way, we are back to the case of a single market. Here's what it looks like for equilibrium number 2 and equilibrium number 3. And this, I tried it last night, trying to do the successive approximations. I didn't, sorry for not bringing them on the slides, but I was motivated by Victor's talk the other day, and it just works much better. Okay. So I think we're ready to move on. Essentially, just let me wrap up here. The NFXP and MPEG implementations of MLE is supposed to be statistically efficient, so there's some debate about that. But what I wanted to emphasize is also the differences in terms of the implementation. NFXP is computationally daunting as we have to compute all the equilibria, and imagine now you have to think about a big in terms of a bigger model, whether it be many more equilibria, and where it takes more time to solve the equations, of course. Okay, and you need to do that for all the different parameters, and then find maximum of this discontinuous likelihood function is going to be a challenging thing. MPEG is computational faster in this case, but you may get stuck in local minima. And the idea here is you don't really have to compute the equilibria, all the equilibria for all the different trial values of the parameters and the investment probables, just have to be in equilibrium at the converged solution. Two-step estimators computational are very fast, right? You just compute the CCPs, throw them into the best response function. That's your likelihood. You maximize this pseudo likelihoods globally. Cave is going to converge fast. Okay, very, very efficient. NPL should bridge this gap, but can be unstable, at least if you do successive approximation implementation of it. And that could be an issue in models with multiplicity of equilibria. So this is pretty challenging, but very cool, very interesting. And I think I just want to leave the floor to Fedor. It's going to show at the end. This could just going to be even more challenging and interesting as you move to dynamic games.